Hello and welcome to Starlit Science Stories, where we explore the wonders of the universe with a soft voice and sleepy eyes. If you're settling in for the night, you're in just the right place. Whether you're tucked into bed, wrapped in a blanket on the couch, or listening with your eyes already halfway closed, this video is designed to help you unwind, breathe a little slower, and drift into that gentle place between wakefulness and dreams. Now, before we begin our journey beneath the Earth's surface into the hidden, humming world below the crust, I'd love to ask for a small favor. If you find yourself enjoying this quiet corner of science, consider tapping the like button or subscribing so you don't miss any future bedtime explorations. It really does help this little channel grow, and it means a lot. Also, if you're still awake enough to type a comment, I'd be so curious to know, where in the world are you listening from tonight? And what time is it for you right now? I love seeing all the sleepy scientists scattered across time zones, listening together in our own quiet way. I do hope this video is soothing enough to help you fall asleep, but there's always the small risk that it might be too fascinating. If you do end up staying awake, at least you'll come away knowing a bit more about the strange and resilient life forms living deep beneath our feet, which, all things considered, is a pretty good trade for a missed hour of sleep. So, take a deep breath in, let it go, and let's begin our descent, slowly, calmly, into the mysterious world beneath the Earth's crust. Beneath your feet at this very moment lies a world you rarely think about. It's not just dirt and rock. It's a layered masterpiece of planetary architecture, stretching down for thousands of kilometers, each level more mysterious and extreme than the last. Tonight, we're going on a journey downward, not too fast, don't worry, through the Earth's layers. We'll pass through places where the pressure is intense enough to crush submarines and the heat could boil steel. It's not exactly a spa down there, but somehow, some things live in it. Let's start with the bit we're most familiar with, the crust. This is Earth's outermost shell, and it's surprisingly thin. Imagine peeling an apple. The skin of the apple is the crust. On land, it's usually between 30 to 50 kilometers thick. Under the oceans, it can be as thin as just 5 kilometers. That's basically the difference between a hiking trail and a subway ride. And yet, this fragile crust is where all known surface life, including you and me, has evolved, walked, danced, and occasionally stubbed its toe. The crust is made up mostly of igneous rocks like basalt and granite, mixed with sedimentary layers and bits of metamorphic rock. It floats ever so delicately on the mantle beneath it, like crackers on a very hot, gooey cheese dip. Which brings us to our next stop, the mantle. Once you break through the crust, you enter the mantle, which stretches down to about 2,900 kilometers below the surface. That's a long fall, so let's take our time. The mantle is split into two parts, the upper mantle and the lower mantle. The upper part is partially molten and very slowly moves, which causes the tectonic plates above to drift. This is the engine behind earthquakes, volcanic eruptions, and the slow rearrangement of continents. So, you can thank the upper mantle for Pangaea and for Iceland being on top of a volcanic hotspot. As you go deeper into the mantle, it gets hotter and more pressurized. By the time you're down around 1,000 kilometers, the temperature is well over 2,000 degrees Celsius, and the pressure is enough to make a diamond feel a little tense. Interestingly, despite the heat, the lower mantle is mostly solid thanks to the immense pressure locking everything in place. The rocks here behave plastically, like very stiff putty, moving at a pace of about a few centimeters per year. If you've ever watched paint dry, congratulations. You've just simulated the speed of the lower mantle. And then at the core, things start getting downright dramatic. The outer core begins at around 2,900 kilometers down and extends to 5,150 kilometers. This layer is composed mostly of liquid iron and nickel. It's not just a hot puddle, though. It's a swirling, dynamic sea of molten metal, and it's responsible for something pretty important: Earth's magnetic field. That field, which quietly shields us from deadly cosmic radiation, exists because the liquid outer core spins and convects, creating electric currents. These currents produce the geomagnetic field, which in turn guides migratory birds, protects astronauts, and makes compasses slightly more useful than just staring at the sun. Now, if we keep going, we reach the inner core, a dense, solid sphere of iron and nickel, sitting right in the center of the Earth, about 6,371 kilometers from the surface. Temperatures here may reach up to 5,500 degrees Celsius, roughly as hot as the surface of the sun. But the pressure is so extreme, over 3 million times the pressure at sea level, that the iron remains solid despite the heat. The inner core doesn't melt. It's like trying to boil a pot of soup inside a hydraulic press. Just know, even though we talk about these layers like distinct zones, Earth isn't layered like a cake you can cut with a knife. The boundaries are fuzzy, dynamic, and constantly shifting. Earthquakes send shock waves through these layers, and by studying how those waves travel, scientists can map the invisible structure beneath us. It's like using ultrasound on a planet. So, where does life fit into this geological lasagna? Well, life, it turns out, is surprisingly cozy in some of these environments. The crust, especially the deeper parts, is home to something called the deep biosphere. This is where microbes eke out an existence in dark, isolated rock fissures, surrounded by minerals and fluids rich in hydrogen, sulfur, and other tasty elements, if you're a microbe, that is. Some of them live so deep that they're cut off from the surface entirely, possibly for millions of years. These microbial pioneers live without sunlight, without fresh air, and under crushing pressure. Many survive by chemosynthesis, using chemical reactions to generate energy rather than sunlight, like plants do. It's like photosynthesis's grittier underground cousin. And because these critters live so slowly, some might only divide once every 1,000 years, they're among the most patient life forms on the planet. The exact lower limit of life is still a mystery. Scientists have found microbes living more than 5 kilometers below the surface in places where the temperature exceeds 120 degrees Celsius. That's hot enough to kill most things on the surface, but these little champions have proteins and membranes adapted to the heat, and they just keep doing their microscopic thing, replicating, metabolizing, and being quietly amazing. Interestingly, we've barely scratched the surface of what's down there. Some researchers believe that the biomass of the deep biosphere could exceed that of all surface life combined. That's a staggering thought. More living matter hidden in the rocks below us than in all the forests, oceans, and grasslands above. So, next time you take a walk outside, consider this. Beneath your every step, the Earth isn't just a ball of rock. It's layered with wonder, humming with energy, and if you go deep enough, teeming with life that doesn't need light to live. It's a reminder that even in the darkest, hottest, most pressurized places imaginable, life finds a way, and it does so very, very slowly. Deep beneath our feet, where sunlight has never shone and the air is more myth than memory, there are creatures, tiny, tenacious, and absolutely thriving. If you thought penguins in Antarctica or fish at the bottom of the Mariana Trench were extreme, let me introduce you to the true heavyweights of the survival game, the deep dwellers. These organisms don't just live in extreme environments, they throw house parties in them. Let's start with the stars of the show, extremophiles. The name says it all, extreme lovers. These are organisms, mostly microorganisms, that have not only adapted to conditions that would kill almost anything else, but in many cases, they require those conditions to live. Imagine if you could only survive in a sauna that's also under a mountain and infused with toxic gases, and you liked it that way. There are many different types of extremophiles, each specialized for a particular flavor of extremity. Thermophiles, for instance, love heat, not just warm, but hot. We're talking temperatures above 60 degrees Celsius and often much higher. These organisms can be found in deep-sea hydrothermal vents, hot springs, and you guessed it, deep underground, where Earth's internal heat creates their own little sauna paradise. Then there are piezophile, from the Greek piezo, meaning pressure. These creatures thrive in crushing conditions, like those found kilometers beneath the Earth's crust or at the bottom of the ocean. Imagine living under the weight of thousands of elephants and not only being fine with it, but needing it to feel comfortable. And then we have the chemolithoautotrophs. It's a mouthful, but their name is a precise job description. Chemo for chemical, litho for rock, auto for self, and troph for feeder. They quite literally feed themselves using chemicals from rocks. They don't need sunlight. They don't need organic matter. They extract energy from things like hydrogen, sulfur, iron, and ammonia. Essentially, they look at a lump of mineral and think, lunch. These organisms are key players in what scientists call the deep biosphere, a vast and mostly invisible ecosystem that may account for a huge proportion of life on Earth. Estimates vary, but some researchers believe that up to 70% of Earth's microbial life exists in the subsurface, buried beneath rock and going about its incredibly slow but remarkably stable business. Now, if you're wondering how they survive without sunlight, it all comes down to chemosynthesis. Unlike plants, which convert sunlight and carbon dioxide into energy through photosynthesis, these microbes use chemical reactions. For example, they might oxidize hydrogen gas released by radioactive decay in rocks or convert iron compounds into usable energy. It's like solar power, but with a hard hat and a pickaxe. One of the most interesting habitats for these underground microbes is within rock pores and fractures. Deep in the crust, rocks like granite and basalt aren't solid fortresses. They have tiny cracks and pockets filled with fluid. These microscopic spaces become microbial condos. Within these crevices, life is slow, yes, but astonishingly persistent. Some microbes form biofilms, communities glued together by a slimy matrix that keeps them safe and hydrated, even when food is scarce and conditions are harsh. Many of these life forms are anaerobic, meaning they don't need oxygen. In fact, for some, oxygen is toxic. Instead, they rely on other electron acceptors like nitrate, sulfate, or even carbon dioxide. These are the kinds of organisms that challenge our assumptions about what life needs to exist. Light? Nope. Air? Not necessary. Space? They'll live inside a rock smaller than a sugar cube. One of the most fascinating things about these deep-dwelling microbes is how slowly they live. And I don't just mean they're laid back. I mean they operate on timescales that make glaciers look speedy. Some may only divide once every few hundred or even 1,000 years. Their metabolism is slow to a crawl, sustained by an incredibly frugal energy budget. It's not a sprint or a marathon, it's an eternal shuffle. But in their environment, that's enough. These slow metabolisms are part of why scientists think the deep biosphere is so massive. It's full of organisms that don't do much but don't die either. They're just there, existing for eons, the microbial equivalent of hanging out in your basement for 3,000 years with a single granola bar and somehow still not finishing it. Now, you might be wondering, how do we know all this? After all, We can't exactly pop down to 5 kilometers below the surface with a petri dish and a flashlight. Scientists study these organisms using deep boreholes, mine shafts, and drill cores from scientific expeditions. One of the most ambitious projects is the Deep Carbon Observatory, which has spent years studying how carbon, and the life that depends on it, exists in the deep earth. Researchers have retrieved samples from kilometers below the surface and found living microbes, even in environments previously thought completely sterile. Some of the deep biosphere's residents are so unique that they've never been observed on the surface. They may represent entirely new branches on the tree of life, ones that evolved in isolation for hundreds of millions of years. And just to keep things interesting, some microbes have been found feeding on radioactive decay. That's right, certain bacteria actually live off the energy released by radioactive elements in rocks. It's not a huge amount of energy, but apparently it's enough. They are like the nuclear reactor custodians of the microbial world, quietly going about their work in the deepest, darkest corners of the planet. So, the next time you picture life on Earth, don't just think of forests and oceans and the fluttering wings of birds. Think of the microbes buried miles below the surface, clinging to the edges of rocks, feeding on gases and minerals, and moving through time with the patience of stone. They may be tiny, they may be slow, but they are among the most remarkable survivors on this planet. And they remind us that life, no matter how small, has a remarkable way of showing up in the most unexpected places. In the deepest reaches of the Earth, far from the noise and sunlight of the surface world, scientists made one of the strangest discoveries in the history of biology. They weren't hunting for life, just drilling through ancient rock in the name of mining and science. But deep inside a South African gold mine, at nearly 3 kilometers below the surface, they found something unexpected: life. One single organism, living completely alone in a hot, dark pocket of the Earth where no one imagined anything could survive. Its name is Candidatus desulphurutus audaxviator. A bit of a mouthful, but bear with me because this little microbe has earned every syllable. First, let's set the scene. The mine in question is the Mponeng Gold Mine in South Africa, one of the deepest human-made holes on Earth. It's so deep that the temperature of the rock can reach 70 degrees Celsius, hot enough to make the walls sweat. Miners have to be cooled by ice slurry to keep working. The pressure is intense, the air is thin, and yet, in a tiny water-filled fracture in the rock, researchers found something alive. Now, desulphurutus audaxviator isn't just any microbe. It's what scientists call a monoculture, the only species living in that particular environment. No community, no food chain, no other microbes, no sunlight, no photosynthesis, no oxygen, just one lone species sustaining itself in an ancient, sealed-off world. The name audaxviator comes from Latin, meaning bold traveler. It's a nod to Jules Verne's novel Journey to the Center of the Earth, in which an inscription reads, "Descend, audax viator," or "Descend, bold traveler." And really, could there be a better name? Because desulphurutus is about as bold as microscopic life gets. This little organism lives by a chemical process known as sulfate reduction. It takes energy from breaking down sulfate compounds in the surrounding rock, using hydrogen as a fuel source. The hydrogen, in turn, comes from the radiolysis of water. That is, water molecules being split apart by natural radiation from uranium, thorium, and potassium in the rock. It's a kind of nuclear-powered metabolism tucked into a crack in the earth. And here's the amazing part. This life form doesn't rely on anything from the surface, nothing from photosynthesis, nothing from plants or animals. It's an entirely self-sustaining system, powered by water, rock, and radiation. If aliens came to Earth and asked to see the most independent life form we've got, this would be a strong contender. In 2008, when scientists sequenced the genome of Desulfurutus, they found that it contained nearly everything it needed to survive on its own. Genes for repairing DNA, for metabolizing hydrogen and sulfate, for dealing with high temperatures and heavy metals. It's a biochemical Swiss Army knife, all in a single-cell body. What makes this discovery so thrilling, apart from the whole living alone at the bottom of the world thing, is what it tells us about life in general. If something can survive in complete isolation, with no organic input from the surface, what does that mean for life elsewhere? It shifts the goalposts dramatically. For decades, scientists searching for extraterrestrial life have looked to places like Mars, Europa, one of Jupiter's moons, and Enceladus, orbiting Saturn. These are cold, dark worlds, harsh by our standards, but they also contain rock, water, and energy sources. Sound familiar? It turns out you don't need a sunny meadow to support life. You just need chemistry and time. Desulfurutus has become a poster child for astrobiology, the study of life in the universe. It proves that microbes don't need much to survive. And in doing so, it raises a hopeful possibility. Maybe the universe is teeming with life, just not the kind we're used to. Now, let's take a moment to appreciate how remarkable it is that we even found this organism in the first place. It wasn't part of a grand mission to explore the deep biosphere. It was more of a lucky coincidence, the result of mining operations and curious scientists with a knack for asking odd questions like, what's living inside this boiling rock? This chance encounter has led to a broader appreciation for how rich and strange Earth's inner ecosystems really are. It's as if the planet has been keeping secrets, tucking away tiny, resilient life forms in its crust like little time capsules. And if Desulfurutus is down there, what else might be? Microbial ecosystems might be thriving in deep pockets all over the world, completely cut off from sunlight, isolated for millions of years. Some might be thriving in ancient aquifers, others nestled in deep-sea vents or continental fracture zones. There could be entire microbial metropolises quietly humming away beneath our feet, and we'd never know unless we dug down and looked. But even if Desulfurutus remains a loner, its story is enough because it tells us that life doesn't just adapt, it persists. It endures. It finds ways to survive, not just in the hard places, but in places that seem entirely uninhabitable. And it does so without fanfare, without fuss, just a little microbe deep underground, doing its thing. So, next time you're walking around, staring at the ground, remember that somewhere 3 kilometers beneath the Earth's surface, there's a microscopic, bold traveler living a quiet, nuclear-powered life in the dark. And if that's not inspiring, well, it's at least pretty cool for bedtime. Deep underground, where sunlight has never reached and the silence is absolute, life has found a way not just to exist, but to make a home. And I don't mean lounging around in cozy caves or hot springs. I mean living inside the very rocks themselves, thriving in the tiniest pores and cracks, nestled in spaces smaller than the width of a human hair. This is the realm of the living rock, where microbes call solid stone their address. If you thought your apartment was small, imagine squeezing your entire life into a bubble of water trapped in a grain of basalt. To understand how anything can live in such a place, we first need to talk about the rocks themselves. The Earth's crust, particularly the oceanic crust and deep continental crust, is made up of all kinds of igneous and metamorphic rocks, basalt, granite, gneiss, and more. At first glance, these rocks seem lifeless, inert, but under a microscope, they reveal a hidden architecture of microfractures, pores, and mineral surfaces. These spaces, although tiny, can hold water. And wherever there's water on Earth, life tends to follow. Microbes that live in rock are called endoliths, literally, within stone. These organisms live not on the surface of rocks, but inside them, in microscopic pockets of water or along mineral surfaces. The rock isn't just a shelter, it's also a pantry. Many of these microbes extract energy by reacting with minerals in the rock itself, using iron, sulfur, or even manganese as part of their metabolism. For example, some bacteria oxidize ferrous iron, Fe superscript 2, to ferric iron, Fe superscript 3, gaining energy in the process. Others reduce sulfate to hydrogen sulfide. These chemical reactions might not sound exciting, but in the microbial world, they're the equivalent of cooking up a hearty stew. One of the fascinating things about life in the crust is how slowly it all happens. These microbes don't reproduce in hours like their surface-dwelling cousins. In some parts of the deep biosphere, a single microbial cell might divide only once every several hundred or even thousands of years. That's right. Some microbes have been alive since before the invention of agriculture, just hanging out in their mineral crevices, slowly nibbling away at chemical energy. Why so slow? Well, deep rock environments are low-energy systems. There's not much to eat, not much room to grow, and conditions are tough. High pressure, high temperatures, and limited nutrients. Microbes that live here have to be models of efficiency. Their metabolisms are minimalist, their growth strategies patient. In fact, it's entirely possible that some of these organisms are living in a kind of ultra-slow motion, suspended in geological time. Despite their sluggish pace, these rock-dwelling microbes are anything but unimportant. Scientists believe they play a vital role in Earth's biogeochemical cycles, the processes that move elements like carbon, sulfur, and nitrogen through the planet's systems. Deep microbes help weather rocks, recycle nutrients, and even contribute to long-term carbon storage. In a way, they're like the quiet maintenance staff of Earth, working unseen in the background, keeping the planetary machinery running smoothly. They also form biofilms, which are communities of microbes glued together by a protective matrix. In the deep biosphere, biofilms help microbes stick to rock surfaces, trap nutrients, and resist harsh conditions. They can even form slimy layers on the walls of deep fractures, acting like miniature microbial cities with structure and function. Another fascinating element of life inside the crust is the symbiotic relationships that can form. Some microbes work together to exchange nutrients or to break down minerals that neither could manage alone. In these tiny rock pores, cooperation can be a matter of survival. One species' waste might be another's dinner. It's the ultimate in microbial recycling. And what about the conditions? Well, as you go deeper, the pressure increases dramatically, around 1,000 times greater for every 10 kilometers down. Temperatures rise too, sometimes exceeding 120 degrees Celsius. For most surface organisms, that would be a death sentence. But the microbes of the deep are adapted to thrive in these extreme environments. Some have heat-resistant proteins that don't unravel in the heat. Others have specialized cell membranes that remain stable under pressure. Their DNA repair mechanisms are robust, able to withstand the occasional burst of radiation from naturally decaying elements in the rock. These aren't just survivors, they're specialists, honed by billions of years of evolution to endure conditions that seem utterly inhospitable. And still, they remain largely invisible. Even with the best technology, it's difficult to sample the deep crust without contaminating it. Scientists use specialized drilling equipment and ultra-clean techniques to ensure they're not just detecting surface bacteria that hitchhiked on the drill bit. It's painstaking work, but the discoveries are worth it. Every new sample, every unexpected genome, adds another piece to the puzzle of Earth's deep biosphere. And that puzzle keeps getting more intriguing. Some microbes discovered in deep rock samples have no close relatives on the surface. Others possess genes for functions that scientists still don't fully understand. There's a growing sense that the deep biosphere isn't just an extension of life above, it's its own unique realm with its own evolutionary paths. This also raises tantalizing questions. How long has life been living inside the crust? Could it have originated there? Some researchers argue that early Earth may have been so hostile on the surface, bombarded by meteors and UV radiation, that life might have started underground, protected by rock, nurtured by chemical gradients, and slowly working its way outward. It's a humbling thought that while we tend to picture life as a thing that flourishes in the light, the first spark may have glowed in the dark. So, the next time you pick up a rock, just consider, it might once have been home to a thriving microbial community. It might still be. Life isn't always where we expect it. Sometimes it's locked away in silence, slow, stubborn, and steady, quietly proving that even the hardest stone can be full of life. Beneath our oceans, under the continents, and deep into the Earth's mantle lies something remarkable, a hidden ocean. Not a vast, sloshing sea like the Atlantic or Pacific, but a world of water locked within minerals, trapped in rock, and soaked into microscopic pockets in the crust and mantle. And while it may not be the kind of ocean you can swim in, it could contain more water than all the surface oceans combined. Let's start with what we normally think of when we say water. The oceans we know and love are just a thin film on the surface of our planet. In total, they cover about 70% of the Earth's surface and hold around 1.4 billion cubic kilometers of water. That's a lot of liquid, but it turns out the Earth is incredibly greedy when it comes to storing water in unexpected places. Deep beneath the surface, at depths of hundreds of kilometers, certain minerals can trap water molecules inside their crystal structures. This isn't free-flowing water. There are no underground lakes sloshing around down there like lost aquariums. Instead, this is bound water, hydrogen and oxygen atoms held tightly within the minerals themselves. One of the key players in this deep hydration drama is a mineral called ringwoodite. It's a high-pressure form of olivine, a mineral that's common in Earth's upper mantle. Ringwoodite only forms at extreme depths, between about 525 and 660 kilometers below the surface, in a zone geologists call the transition zone of the mantle. That's where pressure and temperature conditions are just right for this mineral to act like a sponge. In 2014, scientists made a stunning discovery. They found a diamond, formed deep in the Earth, that contained a tiny inclusion of ringwoodite. Even more amazing, that piece of ringwoodite held water, not droplets, but actual hydroxide ions locked into its crystal lattice. It was direct evidence that the Earth's mantle could hold huge amounts of water in solid form. How much? Well, estimates vary, but some researchers suggest the transition zone of the mantle alone could hold up to 3 times the amount of water currently found in all Earth's oceans. That's a staggering possibility. There is more water inside the planet than on its surface. This hidden ocean isn't just an odd geological footnote. It plays a critical role in plate tectonics, volcanism, and even the carbon cycle. Water lowers the melting point of rock, which helps drive the formation of magma. When tectonic plates dive into the mantle at subduction zones, they carry water-rich minerals with them. As these minerals descend and heat up, they release their water, which causes surrounding rock to melt and form magma. This is why volcanoes often form above subduction zones. Water is acting as a catalyst beneath the surface, silently stoking the fires of geology. But water doesn't just go down, it also comes back up. Over millions of years, water that was once locked in the mantle returns to the surface through volcanic eruptions and hydrothermal vents. In this way, Earth's water is constantly cycling, not just through rivers, clouds, and oceans, but deep through the planet's crust and mantle. It's a vast, slow-moving system that helps regulate the planet's temperature and keeps the surface habitable. Now, where there's water, there's often life, and the deep Earth is no exception. Hydrated rocks create tiny, stable environments where extremophile microbes can thrive. These hidden pockets of water serve as habitats for the deep biosphere. They offer moisture, chemical nutrients, and in some cases, protection from radiation and other surface threats. In places like the Canadian Shield, South African mines, and Finnish bedrock, researchers have discovered ancient groundwater that's been isolated for millions or even billions of years. Some of these water pockets are so old that they predate the dinosaurs, and yet they still support microbial life. These ancient waters are rich in hydrogen and other chemical energy sources, generated by the interaction of water with the surrounding rock. It's a natural chemistry lab, and the microbes that live there, often slow-growing, long-lived, and metabolically conservative, have adapted to survive in these timeless conditions. Some of these organisms are so uniquely suited to their environments that scientists believe they might represent entirely new branches of life. In studying them, we're not just learning about Earth, we're glimpsing what life might look like elsewhere in the universe, in places where sunlight never shines. That's one of the most compelling aspects of the Earth's hidden ocean. It doesn't just tell us about geology, it offers a blueprint for astrobiology. If Earth can hide an ocean in its mantle, why not other planets? Moons like Europa and Enceladus are already suspected to have subsurface oceans, but even rocky planets like Mars could hold hydrated minerals deep underground. If life can thrive inside Earth's rocks, it could very well do the same elsewhere. Back here at home, we're only just beginning to understand how much of our world is shaped by this internal water. Every volcanic eruption, every tectonic shift, every mountain range owes part of its existence to the subtle influence of water moving beneath the surface. It's easy to forget, when standing on solid ground, just how fluid our planet really is. So, as you lie back and drift off, think about the water you know, the rain tapping on your roof, the rivers winding through the land, the waves lapping on the shore. And then think about the water you don't see, locked inside crystal structures, drifting slowly through ancient rock, quietly shaping the earth from within. Because beneath the mountains and the oceans, beneath the cities and forests, there's another ocean, a secret one. And in its quiet depths, life stirs. Time is a funny thing in the deep earth. On the surface, we mark its passing with sunrises and sunsets, seasons, birthdays, and forgotten cups of tea. But down below, far below, time is something else entirely. It's slow, heavy, and patient. Down there, even microbes measure their lives not in hours or days, but in centuries. So, when we ask how long life has existed beneath the Earth's crust, we're stepping into a different kind of timeline, one measured not by clocks but by stone. To understand just how ancient deep Earth life is, we have to look at the fossil record, not the kind with dinosaur bones and petrified leaves. The fossils we're talking about are microscopic, sometimes just patterns of carbon, sulfur, or iron left behind by organisms that lived billions of years ago. Some are little more than chemical whispers of life, tiny traces etched into ancient rock. And yet, they tell a story as grand as any saga of kings and empires. One of the most astonishing discoveries in this field came from Western Australia, in a chunk of rock over 3.5 billion years old. Scientists found what appeared to be the fossilized remnants of microbial life, locked within ancient hydrothermal vent systems. These weren't organisms sunbathing on the surface. They were living deep below it, using chemical energy from the Earth's interior to survive. This raises a profound question. Could life have originated underground? It's a possibility that scientists are increasingly considering. The early Earth was a chaotic place, bombarded by meteors, riddled with volcanic activity, and lacking a protective ozone layer. The surface, especially in the planet's first billion years, wasn't exactly what you'd call hospitable. But underground, that was a different story. Beneath the surface, the temperature was more stable, radiation levels were lower, and chemical gradients, energy sources, essentially, were abundant. It's entirely possible that life didn't emerge in shallow seas as once thought, but instead began within the crust, in the safety of rock fractures and mineral pores, slowly evolving and expanding upward as the surface became more forgiving. Even today, deep life persists in places untouched by surface events. Massive asteroid impact? No problem. Ice age? Still warm down here. A solar flare that knocks out satellites. The microbes 4 kilometers below the surface won't even notice. This kind of biological isolation means that some microbial lineages might have been evolving independently for hundreds of millions or even billions of years, separate from surface ecosystems. What's even more astonishing is how old some of these living systems appear to be. In mines in South Africa and Canada, scientists have found ancient water, fluid trapped in rock fractures, cut off from the surface for hundreds of millions of years. In these waters, they found microbial communities that appear to have been living continuously in isolation, feeding on hydrogen and sulfate, generating energy in the dark like tiny biochemical engines. In some cases, these microbes haven't seen the sun since before the first fish wriggled through the seas. Some may have been around since the days of the first multicellular organisms, back when life on the surface was still figuring out how to grow limbs. And it's not just the microbes that are old. The rocks themselves serve as time capsules. By studying isotope ratios and mineral inclusions, scientists can track the chemical signatures of life going back billions of years. Even when the organisms are long gone, the patterns they left in the rock, like biofilm textures, elemental imbalances, or trapped gases, can reveal that life once wriggled or metabolized there. This is where geology and biology intertwine in a kind of scientific poetry. The stone tells the story, and we just have to learn how to read it. What's perhaps most beautiful about the deep biosphere is its constancy. It's not flashy. It doesn't change rapidly. While surface ecosystems rise and fall with climate shifts, extinction events, and evolutionary bursts, the deep biosphere just persists. It endures in slow motion with a kind of microbial patience that defies our usual sense of urgency. This slowness might be one of its greatest strengths. Living at such a sluggish pace means deep microbes are incredibly efficient. They waste nothing, tolerate much, and survive on astonishingly little. One study found that some deep bacteria may have energy budgets barely above the theoretical minimum required for life. They're operating at the edge of what biology allows, and still they thrive. It also means that evolution down there could follow a different rhythm entirely. With such slow reproduction, mutation rates would be low, and natural selection would act on a much longer timescale. This might lead to a form of molecular conservatism, where some genes or proteins have changed very little over eons. It's like biological deep time, a living memory of early Earth, encoded in cells that never left the underground. As researchers uncover more about these ancient ecosystems, it opens up new possibilities, not just for understanding Earth's history, but for searching beyond it. If life started underground on Earth, might the same be true elsewhere? Planets like Mars may have lost their surface water long ago, but could still harbor liquid reserves deep below. If they do, and if chemical gradients are present, it's not unreasonable to think that life might be hiding there, quietly metabolizing away in its own version of deep time. So, The next time someone asks when life began, or how long life has been thriving on Earth, you might gently suggest that the answer lies not in the fossils of dinosaurs or the bones of early humans, but in the silent, stubborn microbes buried in the crust. Life has been down there for a very, very long time. It has watched continents drift, mountains rise and fall, species come and go, and it's still there in the darkness, waiting patiently for the next million years. Because in the deep Earth, time isn't something to race against. It's something to settle into, like bedrock or like sleep. What lies beneath our feet doesn't just tell us about Earth, it whispers secrets about other worlds, too. If life can thrive in the pitch black, high pressure, high temperature depths of Earth's crust, where no light penetrates and energy is scarce, then why not on other planets or moons? It's not just a poetic question, it's one that has changed the course of modern astrobiology. For a long time, scientists searching for extraterrestrial life focused on finding Earth-like conditions, warm temperatures, liquid water on the surface, and perhaps a cozy atmosphere with some breathable oxygen. The classic Goldilocks zone idea, where conditions are just right, made sense when we imagined aliens as slightly greener versions of ourselves, lounging on Earth-like worlds. But then we started looking inward, not into our souls, necessarily, but into our crust. What we found there, life in total darkness, life without oxygen or sunlight, life eating rocks and drinking radiation, forced us to reconsider our assumptions. Suddenly, the question wasn't could life exist in strange places, but rather, why wouldn't it? Let's start with Mars, our rusty next-door neighbor. Its surface today is barren, cold, and dry, with a thin atmosphere that offers about as much protection as a wet paper towel. But billions of years ago, Mars had rivers, lakes, and perhaps even oceans. Evidence of past water is written across its landscape in the form of dried-up riverbeds and sedimentary layers. That water is mostly gone from the surface now, but could some of it still exist underground? There are hints. Radar data from orbiters have suggested there may be briny subsurface lakes beneath the Martian South Pole. Salty water can remain liquid at lower temperatures, and if it's down deep enough, geothermal heat from Mars's interior could keep it from freezing solid. That's right, Mars might have its own secret aquifers hidden from the brutal surface environment. And where there's liquid water, there's potential for life. If microbes on Earth can survive kilometers underground, feeding on hydrogen and minerals, there's no reason Mars couldn't host similar life forms. The Martian crust is known to contain iron-rich minerals, sulfur compounds, and perhaps even pockets of methane. That last one, methane, is especially interesting because on Earth, it's often associated with microbial activity. There are geological ways to produce methane, of course, but the fact that we've detected seasonal spikes in Martian methane has some scientists scratching their heads and quietly wondering if something might be burping below the surface. Then there's Europa, one of Jupiter's icy moons. Surface temperatures there hover around minus 160 degrees Celsius, and the surface is covered in thick ice. Not exactly inviting. But beneath that frozen shell is a liquid water ocean, likely kept warm by tidal flexing. Essentially, Europa gets squeezed and stretched by Jupiter's gravity, which heats its interior through friction. This ocean may be in contact with a rocky mantle, much like Earth's ocean floor. And if that's true, Europa might have something resembling hydrothermal vents, hotspots where heated water, rich in minerals, seeps up from the seafloor. On Earth, these vents are teeming with life. Tube worms, clams, bacteria, and more, all thriving in complete darkness, fueled by chemosynthesis. If Europa has similar vents, it's not hard to imagine microbial life clinging to them, hidden beneath kilometers of ice, going about its business without a clue that the sun even exists. The same goes for Enceladus, a small moon of Saturn. Enceladus is like a frozen snowball with a warm heart. Its icy surface has been seen venting plumes of water vapor, dust, and organic compounds into space through cracks near its south pole. These plumes are believed to originate from a subsurface ocean, and they contain hydrogen, potentially the result of interactions between water and rock. In other words, the basic ingredients for chemosynthesis may be present. NASA and the European Space Agency are now planning missions specifically designed to look for signs of life in these distant oceans. The Europa Clipper, for instance, is set to launch in the coming years and will study Europa's ice shell, ocean, and habitability in exquisite detail. If the deep biosphere on Earth has taught us anything, it's that life doesn't require a sun-drenched paradise to flourish. It only needs chemistry, time, and a little protection from cosmic nastiness. And this brings us to a philosophical shift in how we define the habitable zone. Traditionally, this was a narrow band around a star where a planet could support liquid water on its surface. But with the realization that life could thrive underground, we've had to expand our thinking. Moons and planets once dismissed as too cold or barren are suddenly back in the game, not as Earth twins, but as inner-Earth analogs. Even Venus, written off as a hellish inferno, is under new scrutiny. While its surface is hot enough to melt lead, some scientists wonder whether microbial life could persist in more temperate pockets underground or even high up in the atmosphere, where conditions are slightly less harsh. The chances may be slim, but the lesson is clear. Never underestimate life's ability to show up where it's least expected. We're now living in an age where the search for alien life is as much about geology as it is about astronomy. Instruments that once looked to the stars are now peering beneath crusts and ice caps. Space probes are becoming interplanetary geologists, searching not for grand civilizations, but for humble microbes living slow, quiet lives in the dark. And if we do find life out there, if, somewhere beneath layers of rock or ice, there's a microbe minding its own business on another world, it will almost certainly resemble what we've already found deep within our own planet. Not flashy, not fast, but resilient, tenacious, and quietly remarkable. So, next time you look up at the stars and wonder if we're alone, remember that the answer might be buried, not in space, but in stone. The blueprint for life elsewhere might just be right here, deep below our feet, quietly thriving where no one thought to look. The story of how we discovered life deep beneath the Earth isn't a tale of grand exploration or purpose-built missions. It's much messier than that, in the best possible way. Like so many of science's most surprising revelations, it began with a bit of curiosity, a lot of drilling, and more than a few accidents. For decades, humans have been digging into the Earth, not to search for life, but for things like gold, oil, and answers to geological questions. It turns out that the tools and tunnels we've used to pull treasure from the ground have also opened windows into the hidden world below. In fact, much of what we know about the deep biosphere comes from mines, oil wells, and scientific boreholes, the laboratories of the underground. Let's start with mining, where people have always gone to extraordinary lengths and depths to extract the Earth's riches. In South Africa's gold mines, for instance, workers descend several kilometers underground in search of precious metal. It's hot, it's cramped, and it's dangerous stuff, but it's also an incredible opportunity for science. In these extreme environments, geologists and microbiologists started noticing something peculiar: water, sometimes millions of years old, trapped in fractures within the rock. And that water wasn't sterile. Instead, it was teeming with microbes, tiny organisms that had never seen the surface, isolated for geological ages, somehow alive and thriving in the dark. This is how Desulfurutus audaxviator was discovered, a single-species ecosystem found nearly 3 kilometers down in the Mponing gold mine. It wasn't just surviving, it was thriving, feeding on hydrogen and sulfate in a world of rock and radiation. But mines aren't the only portals into the subsurface biosphere. The oil and gas industry, which drills into the earth to find fossil fuels, has also stumbled upon subsurface life. While searching for oil reservoirs, drilling operations often bring up core samples and fluids from deep underground. What they didn't expect initially was that some of these fluids contained living organisms. For example, bacteria have been found living in oil wells more than 2 kilometers deep. These microbes are often anaerobic, they don't need oxygen, and halophilic, they love salt. And they've adapted to high temperatures, high pressures, and occasionally the toxic hydrocarbons we've been drilling for. They're not just surviving in crude oil, they're part of the ecosystem that's been shaping it for millions of years. In some cases, they even influence the quality of the oil by breaking down hydrocarbons or producing methane as a byproduct. Then there are the scientific expeditions that have made deep drilling their mission, not for money or resources, but for knowledge. One of the most famous is the Kola Super Deep borehole in Russia. It began in the 1970s as a Cold War-era science project. Drill as deep as possible into the Earth's crust. After nearly 2 decades, the team reached a depth of over 12 kilometers, the deepest hole ever drilled into solid rock. They didn't find hellfire, as some jokes suggested, but they did find water, liquid water, trapped in rock at depths no one had expected it to exist. They also encounter high temperatures, unusual mineral structures, and signs of ancient biological activity. The extreme conditions eventually force the project to a halt, but it remains a scientific landmark, a symbol of human persistence and subterranean curiosity. Meanwhile, other countries have joined the deep drilling party. Japan's Chikuhaken mission and Germany's Continental Deep Drilling Program, KTB, have pushed into the earth to study geology, earthquakes, and, yes, microbial life. These projects use sterile drilling techniques to collect uncontaminated samples, which are then analyzed for DNA, isotopes, and chemical traces of biological activity. One of the big challenges in studying deep life is contamination. When you're drilling down into pristine environments that haven't seen the surface in millions of years, even a single microbe from the surface can mess up the data. So, scientists go to great lengths to ensure the integrity of their samples, flame sterilizing equipment, injecting dye markers to trace contamination, and working in ultra-clean labs. It's like trying to study a whisper in a hurricane. But with enough care and patience, the signal of deep life comes through. Sometimes, the most fascinating discoveries aren't even from the drilling itself, but from ancient rocks exposed at the surface through tectonic uplift. In places like Greenland, Canada, and Western Australia, some of the oldest rocks on Earth can be found above ground, revealing microbial fossils and biosignatures dating back billions of years. These clues help us piece together the history of life beneath the crust, when it started, how it survived, and how it changed the planet. All of this has led to a radical realization. The deep biosphere isn't just a curiosity, it's a fundamental part of Earth's system. It's massive. Some estimates suggest it could account for up to 20% of Earth's total biomass. It's diverse, filled with lineages of microbes unlike anything found on the surface. And it's ancient, possibly among the oldest forms of life on the planet. Our accidental discoveries through mining and drilling have transformed our understanding of life. What was once thought to be barren rock is now known to be teeming with hidden ecosystems. The idea that life requires sunlight, oxygen, and surface-level comfort has been completely overturned. In fact, The Earth may be more alive inside than it is on top. So, next time you hear about a mine or a deep drilling project, think beyond the machinery and the minerals. Think of the unseen layers of life, the microbial cities hiding in fractures, the ancient water carrying whispers of biology through stone. In the shadows of our deepest excavations, we're not just uncovering resources, we're discovering ourselves and what it really means to be alive on this planet. And all of it began not with a eureka, but with a humble drill and a bit of human curiosity. When we talk about life beneath the Earth's crust, it's easy to imagine it as a niche curiosity. Some microbes here, a bit of geological trivia there. But the truth is far more profound. Deep life isn't just bizarre or fascinating, it's important. It plays a critical role in the workings of our planet, shaping its chemistry, cycling essential elements, and even influencing the atmosphere we breathe. And the implications go well beyond Earth. Let's start with the basics, the carbon cycle. Most of us are familiar with the surface version. Plants absorb carbon dioxide, animals breathe it out, and the ocean soaks up a good portion. But beneath the surface, a quieter, slower carbon cycle is playing out. Deep-dwelling microbes participate in this cycle by consuming and producing carbon-based compounds, often in the form of methane or carbon dioxide. In particular, methanogens, microbes that produce methane as a byproduct of their metabolism, live in deep rock formations and sediment layers. They help convert carbon from rocks and ancient organic matter into methane, which can slowly migrate upward and escape into the atmosphere. On the flip side, methanotrophs, microbes that consume methane, can capture and metabolize this gas before it escapes, acting as a kind of biological filter. This subtle balance between methane producers and consumers deep underground has a direct impact on global climate. Methane is a powerful greenhouse gas, far more potent than carbon dioxide over short timescales. If more of it escapes from the subsurface biosphere due to warming or drilling, it could accelerate climate change. Conversely, understanding and potentially harnessing the abilities of deep microbes to capture or convert methane could offer tools for climate mitigation in the future. Then there's the sulfur cycle, another area where deep life excels. Sulfate-reducing bacteria are common in subsurface environments, and they play a key role in transforming sulfur compounds. These microbes use sulfate as an electron acceptor in their metabolism, converting it into hydrogen sulfide. This may sound like a minor process, but it affects the chemical composition of groundwater, the formation of certain types of ore deposits, and the overall redox state of the crust itself. It's like microbial terraforming on a micro scale, gradually shaping the chemistry of entire geological systems. The deep biosphere also has implications for nutrient recycling. Nitrogen, phosphorus, and trace metals essential to life on the surface often originate from deeper geochemical processes. Microbes in the deep crust can mobilize these nutrients, making them available to other systems through slow, steady cycling. In oceanic crust, for example, microbial communities in basalt can weather rock, releasing nutrients into seawater over long periods of time. This supports surface productivity and maintains ocean chemistry. So, in a sense, the health of surface ecosystems may rely in part on the quiet toil of microbes far below. But perhaps even more intriguing is the idea that deep life challenges our very definition of what an ecosystem is. We tend to think of ecosystems as visible, tangible things, rainforests, coral reefs, deserts. But what if one of the planet's largest ecosystems is invisible and almost entirely inaccessible? The deep biosphere, by some estimates, may rival or even surpass the biomass of surface life. That's not a footnote in biology, it's a fundamental shift in how we understand life on Earth. This has practical applications as well. Deep microbes are already influencing technology and industry. Some species have enzymes that function at high temperatures and pressures, making them valuable for biotechnology, from industrial chemistry to pharmaceutical development. Others produce compounds with antibacterial or antifungal properties, and researchers are actively studying them for potential new medicines. When life evolves in the pressure cooker of Earth's crust, it develops some pretty impressive survival strategies, and some of those strategies could help us solve modern problems. Even more, these microbes may have a role in environmental cleanup. Certain species can degrade hydrocarbons, reduce toxic metals, or even neutralize radioactive waste. Scientists are investigating how these organisms could be used in bioremediation, a fancy term for using life to clean up environmental messes. Imagine harnessing a deep living bacterium that can stabilize uranium waste or digest oil spills. These aren't sci-fi scenarios. They're real areas of research inspired by the resilience of Earth's underground life. And then, of course, there's the philosophical side of it all. Discovering that so much life exists beyond our view, moving at its own pace, completely unaware of us and unaffected by surface events, is humbling. It reminds us that life is not confined to the cozy margins we inhabit. It is persistent, adaptable, and diverse beyond expectation. The deep biosphere shows us that the story of life on Earth is far larger and older than we imagined, and possibly far more universal. Because if life can exist here, inside the Earth, under pressure and heat, in the absence of sunlight, then why not elsewhere? The same principles apply to other worlds. If we find life on Mars or beneath the ice of Europa, or in the crust of some distant exoplanet, it may resemble the microbes we've already met right here at home. And that would be one of the most profound scientific revelations in human history, that we were never really alone, even in the darkness. So, while it may not always make headlines, the deep biosphere matters. It matters for the climate, for our ecosystems, for technology, for medicine, and for our understanding of life itself. It's a world beneath the world, a hidden force that shapes our planet and challenges our imagination. The next time you glance at the ground beneath your feet, remember, it's not just rock and dirt. It's a living layer, quiet and unseen, but vast and vital. And in its patient, subterranean way, it just might be the heartbeat of the planet. And so, we find ourselves back where we began, gazing down, not with the indifference of someone walking on stone, but with the quiet awe of someone who now knows what lives beneath it. We've taken a slow, thoughtful journey through the layers of the Earth's crust, past the rocky boundaries, and into a world where life persists without sunlight, without oxygen, and without haste, a world where microbes dine on minerals, sip hydrogen gas, and measure time in millennia. We've met bold travelers like Diesel Ferrutus Audaxviator, uncovered hidden oceans locked in stone, and ponder the possibility of life stretching from the depths of our planet to the icy moons of Jupiter and Saturn. But as always, the most profound discoveries often lead us back to simple, childlike questions. What kind of life survives in total darkness? How can anything live under that much pressure, in that much heat? Could something, somewhere far from Earth, be doing the same thing, thriving quietly in the shadows of another world? The answers, as we've seen, aren't just possibilities, they're realities, hidden in plain sight beneath our every step. And now, as you drift off, perhaps not yet asleep, but softer in your thoughts, I hope this journey has left you not just relaxed, but quietly amazed that the idea of a vast, living biosphere beneath your bed, beneath your town, beneath the oceans and continents, gives you a comforting sense of connectedness. That even in the deepest dark, life endures. If you've enjoyed this peaceful dive into the strange and beautiful underworld of our planet, please consider leaving a like, subscribing to The Sleepy Scientist, and sharing where you're watching from and what time it is right now. I always love seeing how many minds are wandering together from so many corners of the world. And if tonight's journey has kept you just a little more awake than usual, well, at least you've learned something in the process. Sleep well, fellow explorer. The Earth is alive, and now you know just how deep that truth goes.